Our research is intelligent self-monitoring and signal restoring system for the helicopter turboshaft engines, gas temperature sensor with adaptive predicting. Reliable multi-channel sensor data is critical for safe, efficient operation of modern complex dynamic systems, such as helicopter turboshaft engine, yet of short-term sensor failures of anomalies can compromise diagnostics and control. The development and intelligent self-monitoring and adaptive signal restoring system for analog sensor is essential to ensure real-time foul detection data continuity and the advancement of intelligent aviation diagnostic technologies. Despite advances from statistical anomaly detection to machine learning for sensor diagnostic, analog sensor and helicopter turboshaft engine remain underexplored. Therefore, an integrated intelligent self-monitoring and adaptive restoring system for helicopter turboshaft engine 40 dual thermocouple array is critical for real-time foul detection and data continuity. The proposed system integrated self-monitoring, adaptive prediction, and signal restoration modules to guarantee continuous, reliable data from the helicopter turboshaft engine 14 dual thermocouples gas temperature sensor under extreme condition. By continuously comparing multi-channel signal to detect anomalies using dynamic memory-enabled machine learning for real-time predicting and applying interpolation and adaptive smoothing to correct errors. Based on above, an algorithm for the system's operation is proposed in present in this table. In our research, the pre-processing and self-monitoring modules mathematical description was developed and presented in our article. The adaptive predicting module employs a modified LSTM network enhanced with dynamic stack memory and an anomaly adaptive mechanism using smooth ReLU activation is the author's development activation function to efficient restore missing or distorted gas temperature sensor signal in real time by minimizing computational overhead and Euler influence. A MATLAB Simulink-based simulation stand generated synthetic 14 dual thermocouple gas temperature signals with parameterizable noise and injected short-term failures, then processed them through filtering, multi-channel statistical anomaly detection, integration, and data exchange, signal restoration, and logging and monitoring. The authors obtained Mi-8 MTV helicopter flight test data with TV3117 engine, gas temperature in front of the compressor turbine sensors recorded every 0.25 seconds over 320 seconds at 2,500 meters altitudes, then simulated a short-term sensor failure by zeroing gas temperature values from 225 to 235 seconds, 40 missing samples. After noise filtering and Z normalization, this anomaly zeros remained in the time series, distorting its statistical properties and compromising data sets homogeneity. In the simulation, the modified neural network with dynamic stack memory and adaptive anomaly processing scamplessly restored to the gas temperature values during the 225 to 235 seconds sensor failure and showed in this figure. Red curve is presented for stored data. The evolution metrics confirm that the modified neural network model derives highly accurate reconstruction of the corrupted temperature sensor data and robust anomaly detection with minimal false alarms. Its stable real-time performance and strong predictive capability demonstrate suitability for integration into intelligent onboard monitoring and diagnostic systems for helicopter turboshaft engine. And our research also presented evolution of the modified neural network with dynamic stack memory, effectiveness in a self-monitoring and signal restoring system for a gas temperature sensor, limitation and prospect for future research. The conclusions are presented in this slide. Thank you for your attention.